capacitor. The MOS capacitor, it works in various. Now this is one of the electronic devices concept. I have taken it from different. I've considered a Schottky diode, a metal semiconductor diode in this. However, the MOS capacitor in the MOSFET region is also a metal in a semiconductor region, and this metal in a semiconductor region are of various types, that at equilibrium, at accumulation mode, at depletion mode, and an inversion mode. So for N channel, if we wish, we can think of inversion mode, right? Because in this the voltage is very much greater, and the metal applies at metal we apply a QV voltage, and at the inversion layer we got an inverted charge carriers accumulated. A large amount of charge carriers are being accumulated at the other end of the oxide, and you can see it's an inversion layer because initially the intrinsic charge carrier intrinsic level was below, but with increase in voltage it finally get above the Fermi level of the semiconductor. So that's why it's an inversion. However, in other scenarios, you will see that for accumulation, if it is a peak type channel and the voltage is less than 0, then for minus QV, the accumulation results will decrease the overall level, the conduction level will decrease, the intrinsic level, Fermi level will decrease. The Fermi level of the semiconductor will be equal to that of the QV difference in respect to the Fermi level of metal. However, the intrinsic Fermi level will remain above to the Fermi level of the semiconductor. And here is the valence band. In the depletion region, when it is greater than 0, or yes, you can say that even this is an N channel region, but it's a depletion region. I would say that channel is already created in this region. It is not something that initially there was no channel and that eventually there is a channel. Okay, so if there is a channel and it start increasing, and the intrinsic Fermi level is above to the intrinsic Fermi level of the semiconductor. Okay, so yes, this is the 4 modes of the capacitor, MOS capacitor, which we actually see while performing. Keep these in mind because often you can be asked on the basic question that what are the different mode and what are the working of the different mode and why they show such particular traits of different Fermi levels. So moving forward, okay, here I have. Now let us look at this one great numerical. Why I say it great? Because it actually calculates every parameter that you need to know. An N plus polysilicon gate N channel MOS transistor is made on a p-type silicon substrate, Ne, acceptor ions, the silicon of dioxide thickness in the gate region, and the effective charge interface Qi is given. Find Ci and C minimum for the CV characteristic and find Wm, F mean and dt. So the Fermi level, first of all find the Fermi level. Phi t is Vt natural, Kt by Q is Vt. Natural log of Na over Ni. Na is the doped acceptor ions divided by the intrinsic level. Intrinsic level of silicon, we know it's 1.5 into 10 to the power 10, and Na is mentioned in the question. So we get a Fermi level of 0.329 electron volt. Now if you apply this Fermi level voltage and try to find Wm, that is the width, by this formula, by the formula of 1 by 2 Q by epsilon Na over 5F square will give you Wm, and the formula is, okay, there is one point mentioned that figure 6. Let's take this as a constant not given in the figure, as I haven't shown you the figure here, but let's just take this phi to be, or phi of metal is minus, metal semiconductor is minus 0.95. Q, the charge, is equals to area. Area, this is not area, but we have given the effective interface charge. Effective interface charge into the charge will give you charge per unit area. Initially, I have talked about the capacitance of the oxide, which is equals to epsilon of the oxide upon the thickness of the oxide. The thickness of the oxide is given in the equation, I think, 100 angstrom. Okay, so if you calculate it in terms and convert it into centimeter square, angstrom into centimeter square, it is 0.1 into 10 to the power minus 5. Okay, so you get this formula and substitute, you get Ci. When you get Ci, you will try to calculate V of Fb, which is equals to Fms minus Qi. We have known Qi, we have known Ci. Then we have known phi of Ms, which give me this voltage. Now Qd will be equals to minus Qne into Wm. Substitute the value. Vt is equals to Vfb minus Qd over Ci plus 2f, 2πf. That also we know. Substitute that value. Cd is equals to epsilon s over Wm. Epsilon s is silicon epsilon, which is 11.8 into 8.85. At last, capacitance minimum is the two capacitance that we calculated, and when they are connected in parallel, that's the minimum. If they are connected in series, that will be their maximum. Okay, so finally we have calculated all the value. Here I would suggest you to kindly refer to one of the images, and the formula will be exactly the same, but the earlier images which I have shown you about the depletion layer and inversion layer, kindly look at those formula, those images, and try to get the point that how are these parameters situated there. Okay, some of these like VFB, 5FMS, these are all present in the equilibrium level, you can see from there. Moving forward,